Every level of how a CPU works explained. Level 1. Transistors and logic gates. The building blocks. The absolute beginning. If you think the CPU is just one big magic chip that does everything, you're stuck at level 1. The truth is, CPUs are built from billions of tiny switches called transistors. These transistors are so small you'd need a microscope to see them. In fact, modern CPUs have around 16 billion of them packed into a chip the size of your fingernail. Here's how transistors work in the simplest way possible. A transistor is like a light switch, but instead of your hand flipping it, electricity controls it. When electricity flows one way, the switch turns on. When it stops, the switch turns off. That's it. On or off. 1 or 0. This is called binary, and it's the only language computers actually understand. Now, when you connect a few transistors together in specific patterns, you create something called a logic gate. Think of logic gates like rules. An AND gate says only turn on if both switches are on. An OR gate says turn on if either switch is on. These gates are the basic building blocks that make everything else possible. The old Apple IIe computer from 1983 had only 4,528 transistors. That sounds like a lot, but compare that to a modern MacBook Pro's M1 chip with 16 billion transistors. That's over 3 million times more transistors in the same amount of space. This is why your phone can run complex games while the Apple IIe could barely display simple graphics. But here's what level 1 people don't understand. Having billions of transistors doesn't mean anything if they're not organized properly. You need structure, coordination, and a plan. Transistors and logic gates are just the raw materials. The real magic happens when you organize them into something useful, which brings us to the next level. Level 2, the ALU calculator, basic math machine. Level 2, the arithmetic logic unit. Still pretty basic, but at least we're getting somewhere. The ALU is like a super fast calculator built into the CPU. But here's the thing, it can only do really simple math. Addition, subtraction, multiplication, and some basic comparisons. That's basically it. If you think this calculator is what makes computers powerful, you're missing the bigger picture. Here's how the ALU actually works. You feed it 2 numbers in binary, 1s and 0s, and you tell it what operation you want. Want to add 5 plus 3? The ALU takes those numbers, processes them through its logic gates, and spits out 8. The answer appears on what's called the accumulator, which is basically the calculator's display screen. But the ALU can do more than just basic math. It can compare 2 numbers and tell you which one is bigger. It can shift bits around, which is like multiplying or dividing by 2 really fast. It can perform logical operations like AND and OR that we talked about in level 1. These might sound useless, but they're actually how computers make decisions. Think about it like this. When you're playing a video game and your character's health drops to 0, the game needs to know you died. The ALU compares your health number to 0, realizes they're equal, and triggers the game over screen. That comparison happens through the ALU. The difference between old CPUs and modern ones isn't just about having more transistors. Old CPUs like the 6502 and the Apple IIe had 8-bit ALUs, meaning they could only handle numbers up to 255 at once. Modern CPUs have 64-bit ALUs that can handle numbers up to 18 quintillion. That's a billion times a billion. Massive difference. But here's where level 2 people get it wrong. They think the ALU is doing all the work. The truth is, the ALU just sits there waiting for instructions. It doesn't decide what to calculate or when. It's a tool, not the brain. The real intelligence comes from what tells the ALU what to do, which is where the next level comes in. Level 3, registers and memory, the scratch paper. Welcome to mid-tier understanding. Registers are like tiny scratch paper inside the CPU where it writes down numbers it's currently using. Think of them as the CPU's short-term memory. They hold the values that are about to go into the ALU, or the results that just came out. Without registers, the CPU would have nowhere to temporarily store the numbers it's working with. Here's how this actually works. Imagine you're doing math homework and you need to remember a number while you calculate something else. You write it down on scratch paper, right? That's exactly what registers do. The CPU writes a number into register 0, does some calculations, then grabs that number back when it needs it. Modern CPUs have around 32 general-purpose registers. Each one can hold a single number. Old CPUs like the 6502 had way fewer, which made them slower because they constantly had to fetch numbers from slower memory instead of keeping them close by in registers. It's like having a tiny desk versus a big desk when you're doing homework. But registers are incredibly small. They can only hold a few numbers at once. So where does everything else go? That's where memory comes in. Think of memory like a giant library of books. RAM, which stands for random access memory, is like a cart that holds books you're actively reading. The hard drive or SSD SSD is like the bookshelves where everything is stored long-term. When you open a program, the CPU moves that program from the hard drive into RAM because RAM is much faster to access. Then it moves the specific pieces it needs right now into the cache, which is even faster memory built directly into the CPU chip. Finally, it loads the exact numbers it needs into registers for immediate use. Level 3 people understand this hierarchy. Hard drive is slow but huge, RAM is faster but smaller, cache is even faster but tiny, and registers are the fastest but microscopic. But here's what they're missing. Having all this memory doesn't matter if the CPU doesn't know what to do with it. That requires instructions. Level 4. Instructions and programs. The recipe book. This is where casual knowledge separates from actual understanding. A CPU doesn't just randomly calculate things. It follows a list of instructions, kind of like following a recipe. Each instruction is a simple command like load this number into a register, or add these two numbers together, or save this result to memory. Programs are just long lists of these instructions written in a specific order. Here's what makes this powerful. Every single thing your computer does, whether it's playing a video, loading a website, or running a game, breaks down into millions of these simple instructions executed one after another. The old Apple IIe could only understand 56 different types of instructions. The modern M1 chip can understand 354 different instructions. That might sound like a lot, but they're all pretty simple commands. Let me give you an example. When you click a button in a game, the program has instructions that say, check if the mouse was clicked, load the mouse position, compare it to the button's location. If they match, then run the button's action. Each of those steps is a separate instruction. String together millions of instructions per second, and you get a functioning computer. Instructions live in memory just like data does. When a program runs, the CPU loads the instructions from memory one at a time, figures out what each instruction wants it to do, and executes it. Then it moves to the next instruction. This happens so fast that billions of instructions get completed every single second. There are different types of instructions. Load instructions grab data from memory. Store instructions save data back to memory. Math instructions use the ALU we talked about earlier. Jump instructions let the program skip around, which is how loops and if statements work in code. Branch instructions make decisions based on comparisons. But level 4 people understand instructions exist without understanding how the CPU actually processes them. They know programs are lists of commands, but they don't know the exact steps the CPU takes to execute each one. That's the next level. Level 5. Fetch, decode, execute cycle, the brain's rhythm. This is the technological DNA that powers every single processor ever made. This 3-step cycle is how CPUs actually process instructions, and it repeats billions of times per second from the moment you turn on your computer until you shut it off. Every CPU, whether it's from 1983 or 2025, uses this exact same cycle. It's the fundamental pattern that makes processors work. Here's how it breaks down. Step 1 is fetch. The CPU has a special register called the program counter that keeps track of which instruction to run next. During fetch, the CPU uses that number to grab the corresponding instruction from memory and loads it into another special register called the current instruction register. Then it increases the program counter by 1 so it knows which instruction comes next. Step 2 is decode. The instruction is written in binary, just ones and zeros, so the CPU needs to figure out what it actually means. A part of the CPU called the instruction decoder reads those ones and zeros and translates them into control signals. These signals tell the different parts of the CPU what to do, like send the value from register 0 to the ALU or perform an addition operation. Step 3 is execute. This is where the instruction actually happens. The control signals activate the right components. If it's a math instruction, the values get sent to the ALU and the calculation completes. If it's a load instruction, data gets copied from memory into a register. If it's a jump instruction, the program counter gets changed to a new value, so the next instruction comes from a different location. Once execute finishes, the cycle immediately repeats. Fetch the next instruction, decode it, execute it, then fetch again, over and over and over. The CPU's clock regulates this rhythm. Old CPUs had clocks running at 1 megahertz, completing 1 million cycles per second. Modern CPUs run at 3.2 gigahertz, completing 3.2 billion cycles per second. This is the common technological DNA in every processor. But level 5 people still don't understand the advanced tricks modern CPUs use to go even faster. Level 6. Pipelining and multiple cores. Advanced efficiency. This is where modern CPUs separate themselves from the old ones. Pipelining is like an assembly line in a factory. Instead of waiting for one instruction to completely finish before starting the next one, modern CPUs overlap the steps. While one instruction is in the execute phase, another instruction is being decoded, and a third instruction is being fetched. All 3 steps happen simultaneously, but on different instructions. Think about washing dishes. The old way is wash one dish, dry it, put it away, then start the next dish. Pipelining Pipelining is like having 3 people where one washes, one dries, and one puts away, all working at the same time on different dishes. You still spend the same amount of time per dish, but you finish way more dishes overall because nobody's waiting around. Modern CPUs can pipeline 8 or more instructions at once. This means even though each instruction still takes multiple clock cycles to complete, the CPU is finishing instructions at a rate of several per clock cycle because they're all overlapping. The M1 chip uses aggressive pipelining to achieve incredible performance, but pipelining has problems. What happens when you hit a branch instruction that changes which instruction comes next? The CPU might have already started fetching and decoding the wrong instructions. Modern CPUs use something called branch prediction, where they guess which direction the branch will go and start processing those instructions speculatively. If they guess right, huge speed boost. If they guess wrong, they throw away the work and start over. Then there are multiple cores. Instead of one brain doing all the work, modern CPUs have 4, 8, or even 16 separate processing cores. The M1 chip has 8 cores total, with 4 high-performance cores for heavy tasks and 4 energy-efficient cores for background tasks. Each core runs its own fetch, decode, execute cycle independently. Multiple cores let you do multiple things simultaneously. One core handles your video game, while another core runs your music player, while another handles background downloads. But here's the catch. Programs have to be specifically written to take advantage of multiple cores. Otherwise, all the work happens on just one core, while the others sit idle. Level 6 people understand these optimization techniques, but they're missing the final piece. Level 7, architecture and system design, complete mastery. Level 7, CPU architecture and system design, peak performance understanding. This is where everything comes together. Architecture isn't just one component, it's how all the pieces work as a coordinated system. Modern CPUs are incredibly complex with specialized sections, cache hierarchies, instruction sets, and optimization strategies all working in harmony. The M1 chip isn't just a CPU anymore, it's a system on a chip, or SoC. Inside that single chip, you have 8 CPU cores, a graphics processor with multiple GPU cores, a neural processing unit for AI tasks, separate instruction and data caches, shared cache between cores, memory controllers, and hardware accelerators for specific tasks like video encoding. All of this fits on a chip smaller than a postage stamp. Level 7 people understand instruction set architectures. There are 2 main types, RISC and CISC. RISC stands for Reduced Instruction Set Computer and uses simple instructions that execute quickly and consistently. ARM processors like the M1 use RISC architecture with 354 instructions. CISC stands for Complex Instruction Set Computer and packs more functionality into individual instructions. Intel and AMD processors use CISC with thousands of possible instructions. The trade-offs matter. RISC is more energy efficient, which is why every smartphone uses ARM-based processors. CISC can do more per instruction, but uses more power and generates more heat. Modern processors blur these lines by converting CISC instructions into RISC-like micro-operations internally. Cache architecture is critical. Modern CPUs have 3 levels of cache. L1 cache is the fastest but smallest, split into separate instruction and data caches of 64 kilobytes each. L2 cache is larger but slightly slower. L3 cache is shared between all cores and can be several megabytes. Managing what data lives in which cache level determines performance. Architecture experts understand compiler optimization, how code written in languages like C++ gets translated into machine code instructions. They know about out-of-order execution, where CPUs rearrange instruction order for efficiency. They understand thermal design and power management, because a CPU that overheats throttles itself down to prevent damage. This is where the chip designers, the computer architects, and the people who actually built modern computing operate. They see the entire system from transistors to software working together. That's complete CPU understanding. This video right here? Yeah, prepare to be pissed off. Click it.